Let's look at 2.7 linear inequalities. Now, hopefully we remember our inequality symbols. And each one of these, I'm sure some of you might remember, some of you don't, it's perfectly okay, that they would have a different name just because the direction of the symbol of the inequality, depending what side it was pointing, you either remembered greater than, less than, more than, or greater than or equal to, or less than or equal to. But sometimes it's important to know those words, and I think as we practice them, hopefully we know how to use them. But I really want to just focus on one idea, and that is just looking that all of these to me are honestly the same. Now, with these two, there's one slight thing we need to add, but they're all the same. The way I think about it is that there is an open side and a closed side. That's what I call it. Where it's pointing to, I like to call that the closed and open. Close and open. Close and open. Close and open. This down here just implies equal to, which is your normal equal sign. And we'll have some examples here about truth and false, but we'll get to that. But first, the side that's open is always going to have the bigger number. And I'm just going to go through all of these, just writing bigger on the side that's open. If you remember the actual name, that's great. If not, for now, I really just need you to remember this. The open side's the bigger side. The closed side is the smaller side. The idea is we're going to get to solving linear inequalities. You can see a little bit here what we're going to get to, but we're going to use this idea of smaller and bigger. And that's because once we actually start graphing these inequalities, you're going to have a variable, and you can see a little bit of what I'm talking about. There's going to be a variable on one side and a number on another. And that number is going to be your reference point on a number line. And if you remember, you don't have to have everything labeled 0, 1, 2, 3, -1, so on and so forth. Because at any number on that number line, anything to the left is always, or actually let me use a different color. Anything to the left is always going to be smaller. And that's how you can see why I like using smaller, bigger. Now anything on the right is going to be bigger. And that's the language I want to get used to using. One side's bigger, one side smaller. Same side is bigger, same side is smaller. Just because the direction changed didn't mean the meaning changed. So look at the closed side, still smaller. Open side is still bigger. Now, these two, again, there is that equal to symbol. So maybe you remember this one technically means or, equal to, or, equal to. Same thing with these next two, or, equal to. Forgot to put the 2, so equal to, equal to. Now, or is super important here. Saying or. Because in math, there's or statements and statements. And implies both statements need to be true. Or implies just one of them needs to be true. So sometimes when we're looking at an inequality, we think both of these inequalities or both of these symbols need to be true, which is impossible. It's impossible for something to be bigger and equal to it at the same time. That's why the or symbol is here, because you get to put an inequality and an equality in the same problem. And you're only being asked to satisfy one of them, not both. So if you look here, and this is what I meant, when we get to this example of true or false, and you can pause this video, try to answer these. If you can, great. If you can't, it's great too. You'll be able to see how we go through this. Now, this very first one, it says 15 is smaller, 20 is supposed to be bigger, or equal to. Now, definitely 15 and 20 are not equal to. But I don't need to satisfy both of these statements. I only need to satisfy one of them. So I definitely don't satisfy the equal to part. But 15 is definitely smaller than 20. Hence, this is true. Next. Now I have the other symbol facing the other direction, but the idea is still the same. The left side should be bigger, the right side should be smaller, and they are clearly the same number. So I don't satisfy the inequality in this statement, but I do satisfy the equality. So because I only need to satisfy one of them, that's a true statement. Same thing on the next one. Again, I switch the inequality symbol, pointing left. But again, -3 is not smaller than -3, or -3 is not bigger than -3. So we don't satisfy the inequality, but we do satisfy the equality. Hence, this is true. Now here, -3 is equal to -3. This statement, this symbol, does not have an equality. It strictly says one side needs to be bigger, the other side needs to be smaller. And that is going to be false, because -3 is not bigger or smaller than -3. And here, positive numbers, when you're thinking about a number line, right? Positive numbers on the right of 0, negative numbers on the left. And remember what we said, numbers on the left are smaller, numbers on the right are bigger. So because 2 is positive, I know it's on the right. 5 is negative, I know it's on the left. So clearly this is false. So just to give you an insight on how to interpret these symbols, because they're going to make a difference once we get into graphing these inequalities. Now, like I said on this side, there's only one number to reference. That number is 23. And I'm not trying to write my number line 0, 1, 2, 3, 4 all the way up to 23. 23 is the only number in question here. And because of that, that number, I just put it anywhere on this number line. But then I have to read this statement. X is on the pointy side, which is the smaller side of the inequality. 23 is on the larger side. So that tells me that the X value, the values that can be plugged into X, have to be strictly smaller than 23. And where are the numbers smaller? On the left side. So that means my answers are on the left side of 23. But something you have to ask yourself is, what about 23 itself? Is 23 itself part of this solution? And just like how we did with true and false, you should recognize that 23 is not smaller than 23. But how do I indicate that I don't want it part of my solution, right? So this is a way of showing, eventually this would be the way of showing your solution, but right now we're just graphing this equation, this inequality. How do I show that 23 is not part of my graph? And I do that by using an open circle. And the idea of this open circle is happening at 23. Let's look at another example. And this one's a little different. The only number I have to reference is 4. Now, if you notice, don't focus on what direction. A big misconception that people have with inequalities is, oh, my graph must be in the direction that the symbol is pointing. That couldn't be further from the truth. Sure, that might seem true for this first example, but that's not always the case. For example, here it says x says it has to be bigger than 4. And we know the numbers that are bigger than 4 are on the right side of the graph. And that is different than what the direction of that inequality symbol is pointing. That inequality symbol is pointing to the left, but my true solution is on the right side. So I'm not basing it off the direction. I'm just basing off the statements that we have. The open side's bigger, the closed side is smaller. Numbers that are smaller than 4 are on the left, numbers that are bigger are on the right. But how do I take care of this equal symbol? What does that mean? I'm saying that if 4 was plugged into this x, it doesn't satisfy the inequality, but it does satisfy the equality. So how do I denote that 4 is part of my solution? I just put a closed circle versus an open circle to show that 4 is part of the true statement of this inequality. Whereas 23 was not a true statement, and that's why we put an open circle to imply that it's not true. And this idea of open and closed circle usually go hand in hand with inequality. So these first two, we usually would call them strict inequalities because there's no or statement attached to them. So usually when it comes to strict inequalities, you're going to be dealing with an open circle. And when you have an equal to inequality, you're going to have a closed circle. And all that's telling me is that the number in question is part of my graph. Open circle is saying that that number itself, 23, is not part of my graph. And let's look at a couple more. So if you look at this next one, 17 is my only number to reference. Once again, I just need to read the statement. X is on the open side, which is bigger. And where are the numbers bigger than 17? They are on the right. So when it comes to a graph, I graph all the numbers on the right. And once again, because 17 would not make a true statement for this inequality, I will also leave it as a open circle. Now try the next one. If you want to pause the video, try the next one and see how you do. Now, once again, the only number I have to reference is 4. And then I know x cannot be 4 because that would be a false statement. So if you wanted to, you could already start putting an open circle right at 4. But this says, once again, x is on the pointy side, which is smaller. Where are the numbers smaller on anywhere on the number line? The numbers on the left are smaller. The numbers on the right are bigger. So I'm looking for the smaller numbers. Hence, my solution is everything to your left. Now, that's not the only way, because ultimately we're getting to solving a linear equation. But there's a lot of these small nuances I have to recall when it comes to talking about solving inequalities. And one of those is graphing your solution. But you can also write the solution in interval notation. What is interval notation? Well, it either comes in parentheses or in brackets. And the way an interval works is it only shows you the endpoints. It only shows you the endpoints of your interval. Now, how do I know if I use parentheses or brackets? Well, it's very similar to this open and closed circle. Remember, closed circle implied that your variable can represent that other number in question because it would remain to be a true statement. Versus an open circle implied that that number in question is not part of your solution or part of your graph. Well, there is something very similar in interval notation. And what is that thing? When you see parentheses, that's similar to the idea of an open circle. And what does that mean? I usually just say that the parentheses means that it's not included. And when I say not included, I'm talking about the endpoint is not included. Versus brackets, that endpoint is included. Now, if you look at the examples that we're talking about, sure, we have an endpoint on one side of this graph, but we don't have the endpoint on the opposite. And this is what changes a lot from going from an inequality to an equation, is because the inequality can have many solutions, because 17 does not part of my solution, but 18 is, 19, 18.3, 18.7. There's an infinite amount of numbers, not just between 17 and 18, but continuing forever. All those numbers satisfy our statement. But we need to be able to show the endpoints. But here, if this goes to the right forever, or any of these other examples that are continuing in one direction forever, there is no endpoint. That's where you can use the symbol infinity or negative infinity. Now, something about these infinities, when they are part of your interval, they will never be included in your solution, because the solution is all the numbers that do satisfy the statement. Parentheses and infinity and negative infinity do not do that. So we always use parentheses when it comes to infinity and negative infinity. And one last thing to note, you always want to write your interval from smallest to largest. So input from S and /L, from smallest to largest. So here, in this very first one, like I said, you can pause this video at any moment and try to attempt to write the interval notation for these 4 examples. Now, this very first one, there is no endpoint on our left, but it is continuing in that negative x direction. So I would say the interval starts at negative infinity, and then it stops at 23. It's technically not including 23, but the number that follows immediately before 23 is probably 22.999999. So I don't want to write, I don't want to write 22.99999 because it's the number immediately before 23. So the nicest thing to do is just put parentheses around that endpoint, and it tells you if that endpoint is included or not. So here, negative infinity cannot go plugged in, hence it's not part of my solution. 23 can get plugged in, but that's not a true statement. So instead of putting, I had parentheses. The parentheses is telling me that the 23 is not included. But we use that number instead of thinking about the number immediately before. Now, next one, same idea. 17, and it goes on to positive infinity. And then B, we start from the smallest number, which is 4. Then the largest number is positive infinity. Now, once again, the bracket is telling me that 4 can be part of this solution. In the other examples, that's not the case, but in this one it is. One more, we have negative infinity to 4. And neither are included. Because 4 is not included, so is negative infinity not included. Now, if you have any questions, please reach me out pronto. I can help you there. But this is just to kind of give you an idea of how these inequalities work. But let's jump into the heart of this section, which is solving these linear inequalities. Now, because we are going to be solving, I did want to write some notes for something to remember, right? When you're solving an equation, the major idea was to always isolate your variable on one side of the equation. In this case, it's going to be on one side of the inequality. And remember, the way you moved the terms and factors from left to right in an equation from either high school or elementary or whenever, middle school, whenever you learned this, you always had to balance the equation. And most people remember, do the same thing on both sides. So what do you do to one side? You have to do to another. That's how most people remember some of these rules. But again, we're going to follow all those same ideas. We're going to isolate the variable. We're going to be balancing the equation all the way through. But there's one last major thing that you need to watch out for. And I have it highlighted here. Is that when you're solving these inequalities, there's going to come across a time where you might need to multiply or divide by a negative to the inequality. Now, that's going to cause you to switch or flip the inequality symbol in question. Why do we need to do that? Because when you were balancing an equation in high school, you kept the statement true the entire time. But when it comes to inequalities, it can be tricky to see this step. So we're going to switch the inequality only when multiplying or dividing by a negative. And let me show you what that looks like. Because I can have 2 smaller than 4, which we know is a true statement. But if I go ahead and multiply 2 by negative 2 on the left, and then by negative 2 on the right, that leaves me with negative 4. And then I'm going to put tallies because we don't know if that one's going to stay. But that leaves it with negative 8. Now, if you notice something, 2 was smaller than 4. We started with a true statement. But because I multiplied by a negative, it made the left side negative 4 and the right side negative 8. Now, clearly, this would be a false statement because negative 8 will never be smaller than -4. Sorry, will never be bigger. It's actually smaller. And this is when you have to switch the inequality so that the statement is now true. -4 is bigger than -8. And that happens every time you either multiply or divide by a negative. And you'll have to switch this inequality. So let's do this. Let's do some examples going through all these problems. So to start, now these linear inequalities are just in one variable, which makes them really nice because you just have to isolate one of them. Now, a rule of thumb I follow is start with your terms and then go into your factors. It's almost like doing order of operations backwards, which my goal is to isolate for x. How am I going to do that? Well, I'm going to subtract by 4 to both sides first. Why am I doing that? Because this is a positive 4, and the opposite of 4 is -4. And that's going to slowly help me isolate one side of the equation, which then will allow me to isolate the variable. That gives me -6x. That cancels to 0. And then this becomes 30. Now, the x is not isolated yet. So what do I need to do? I need to divide by -6. That's going to leave me with +1 is smaller than Oh, and one thing to be careful, and I was almost made the mistake. We are dividing by -6. Make sure you put that division symbol there. That's going to be -5. Oh, I'm missing one thing. My x. Which normally we don't write 1x, right? We would just write x. Smaller than -5. Now, it would have been tricky to try to explain the entire graphing part now, but hopefully when we did it on the previous example, it made sense. The only number we have to question is -5. Can -5 be part of the solution? -5 is not equal to -5. Definitely not smaller than that. Hence, we're going to have an open circle at -5. But x is on the smaller side, so it has to be smaller, which means the graph is going to be on the left. Bear with me as I draw this graph. And we can still do our interval notation. Parentheses around all infinities. This graph stops at -5. But -5 is not part of my solution. That endpoint does not satisfy the inequality. So I can just write the interval. Now, hopefully, some of you are looking at this and saying, wait, there's something wrong. Hopefully you caught it by now. And that is that we just finished saying when you multiply or divide by a negative, then equality must switch. And if you notice, I never switched out the inequality. So the true inequality should be x has to be bigger. Now, something that's still true, -5 is still not part of my solution. But now my graph is different because all the numbers have to be bigger than x. Sorry, the numbers that can be x have to be bigger than -5. And those are any numbers to the right of -5. So if I look at this interval, I need to restart it as well because it's on the left side. So starting from -5 and going to positive infinity. Now, one more example. Like I said, hopefully you're pausing these and testing them on your own to see what you're doing wrong or right. Now, once again, I like to take care of the terms before I take care of the factors. Now, what are terms? They're separated by plus or minus signs. Factors are separated through multiplication. Now here, once again, I'm adding 6 because it's negative. That's going to leave me with negative 5t. The x's cancel. Negative 5t is larger than or equal to 30. And then we can divide again. But don't forget, dividing by negative, you have to switch your inequality. So that's going to have to make this less than or equal to. We switch it. It's going to be t. And then negative 5 goes in 30, negative 6 times. Now, to graph this, once again, our closed circle is at negative 6. And our graph is on the left. How did I know this? Because this inequality symbol shows the closed side is the smaller side, the open side is the bigger side. Smaller numbers on the left, bigger numbers are on the right. Hopefully that made some sense. Let's do one more really quick. I take care of the terms first. Which the 5's cancel. Negative 2x is bigger than 10. Same trick again. We're going to divide by negative 2. Your inequality symbol is going to flip. And then the negative 2's simplify. And I'm left with a 5. The only number I have to reference is 5. 5 is not going to be clearly in one of my solutions. So I'm going to write an open circle, and the smaller numbers are to the left. Let me just fix this. Now for interval notation, we start from negative infinity. I forgot to do this example, negative 6. But now I use a bracket because negative 6 is part of my solution. It is equal to negative 6. And similarly on this example, we have negative infinity, stop at 5, close infinity. Sorry, not close infinity, close parentheses. And then something else, another type of examples, and I'll end it here, is compound inequalities. This is when you end up having 3 parts to an inequality, and you have to apply that operation on each side. So for example, the middle part of this graph, I know I can subtract 7. And remember, I have to do it to all 3 sides now. That's going to leave me with negative 2 smaller than or negative 2x plus 7 is less than or equal to 4. Ooh, one thing I wasn't supposed to write the 7 anymore. It is gone. I apologize. But now I'm going to divide every term by -2. And because I'm dividing by a negative, I'm going to have to switch the inequality. Now if I were to graph this, I have two numbers to reference, -2, +1. And if I read this carefully, the closed side says it has to be smaller than 1, but the open side says it has to be bigger than -2. So that means at 1, it's not included, but at 2, it is. And x, if you notice, has to be smaller than 1, which is to the left. And then x has to be bigger than -2. That's going to leave us with the solution here in the middle. And that's essentially how compound inequalities work. It takes multiple inequalities and put them into one. Try to finish this problem here. I will post these notes. If you have any questions, please let me know.